pleasure to introduce our first friendly speaker, Oscar Martinez. So please give me a couple of minutes to read what I prepared, not to forget anything. Okay. Okay, this was intended to be somehow an acknowledgement to this brilliant Argentinian physicist and the scientific father of many of us, inspiring love in science, in hardworking, challenging thinking, honesty, and ethics to all physicists. Oscar Martinez is about to retire, and we think that this opportunity in UFO is an excellent occasion to celebrate in his honor. So let me read a short bio. I will be Oscar Martinez graduated from the Physics Department at the School of Natural Sciences of the University of Buenos Aires, Cuba, in 1976. He completed his PhD at Cuba, working for CITEFA, Scientific and Technical Research Institute for Defense, in 1982. Ultra-short pulse lasers were emerging in those years, which caught his attention, who had to carry out his doctoral training nearly on his own, advisory, and contribute to the training of other colleagues at the time. After completing his PhD program, Oscar made a short stay at Bell Labs, and there he published in 1994, together with Falk and Gordon, one of the highest impact works of his career. Negative dispersion using paired prisms, In that work, a simple configuration of 4 prisms is proposed, introducing negative group velocity dispersion. And this development has 2 highlights, we can say. On one side, the simplicity of the proposal, which is actually Oscar's personal signature, and on the other, that has contributed to allowing the development of commercial femtosecond lasers, which began to be massive, let's say, in the middle or the end of the 90s. Back in Argentina in 1985, he founded his lab at the National Atomic Energy Commission, where he, with the first femtosecond laser based on a passive monologue dye system, was put into operation in the country. Later in this laboratory, studies were carried out on the mechanism of self-phase modulation and self-focusing in the titanium sapphire base. In 1987, he published another work of fundamental importance. The name was 3,000 times rating compressor with positive group velocity dispersion, application to fiber compensation in 1.3 to 1.6 micrometer region. This work proposes a pulse compressor, eventually called the Martinez compressor. After that, you know maybe that the Nobel Prize Gerard Moreau, an inventor of the CPA technique, said in a work in 2006, say this: following the first CPA demonstration, the Rochester group started to look for an ideal match stretcher compressor, and it was realized in 1987 when Martinez proposed a grating compressor with positive group delay dispersion for communication applications. And after examining this device, the Rochester group concluded that Martinez compressor was in fact a match stretcher of Tracy compressor that they were seeking. Martinez compressor idea helped Moreau to complete his development based on pulse amplification after stretching and finally compression. Recognized as a pioneer by international reference community, he became fellow of the Optical Society of America in 1994. In 1992, he moved to the physics department at the School of Sciences, Cuba, and established the Quantum Electronics Laboratory, in Spanish is LEC, with Mario Martinez, Marconi. This fact dramatically impacts this department, helping to strengthen the previously weak experimental physics and contributing to many people's training over the years. Oscar's impact as a professor at the department is also seen in his teaching activity. Together with other members of the department, he contributed to the total renovation of the teaching laboratory equipment, a program called FOMEC. The Argentinians know that. So as a result of his innovative and risky teaching performance, his book Ondas es Física, Waves is Physics, has been widely used as a textbook for physics courses since published. Once established at the LEC, Oscar began to venture into the topics of nano and biophotonics. In 1998, he published with his PhD students laser field enhancement at the scanning tunneling microscope junction measured by optical rectification. This work reports the first direct measurement of the electromagnetic field enhancement around the plasmonic nanostructure used as a contrast mechanism in high-resolution microscopy at the nanoscale. During the 20 years he spent at LEC, he has advised almost 20 PhD students addressing topics such as wideband interferometry, nanolithography, nanoantennas, and super-resolution microscopies. In those years, Oscar also had an intense activity in creating centers and laboratories such as the UTN Laboratory of Optics and Applied Metrology, the Center for Advanced Microscopies, and the Laboratory of Microscopy and Microspectroscopies at UBA. Also, he received prestigious awards such as the Konex Prize for Physics in 2003. I almost done. Just as Oscar's creativity, intellectual, professional, and ethical strength are characteristics of this personality, so are his constant exploration and lack of fear of taking risks. So around 2009, he managed the foundation of a technological spin-off company, Tolke, supported on original developments patented in some cases. For that he won many awards, Konex Prize, Innovar, IB for 50K, and among others. He left the company in 2013 and is still running. Okay, finally, in 2013, Oscar moved to the School of Engineering at UBA. He founded there the Photonics Lab, where he is working now with his students on new projects in thermal lensing microscopy, novel super resolution methods in microscopy, and bio-inspired physics. Among his last works, he is the co-author with Sandra Martinez of SUPPOSE method that overcomes the ill-posed deconvolution problem, allowing standard microscope images to be super resolved by mathematical processing. Okay, so now, again, my pleasure to introduce you. This is the title, Revisiting Compressor After 40 Years to Rescue the Terms Disappear.
Okay, well, thank you, Andrea. Actually, much of what you said I have already forgotten. I only remember the last part, but it's okay. So I want to thank the organizers, not only for inviting me to give this talk, because I had a chance to reconnect with this community I left more than 20 years ago. Except from some, touch and go with Jorge Roca. Sorry, Jorge, it could only be just for very short interactions. So, I had to, 40 years, I figure out it's been 40 years in the prism compressor. And I said, well, let's look at the notebooks. It's fantastic. Notebooks are great because they last more than 40 years. Which I challenge any other storage mechanism. They usually will never last that long. I mean, my thesis was written in a floppy disk. There's no way I can read it, for example. But I can still read my notebooks. So, it was difficult, a hard work. So, the organizers gave me a hard work. I have to pay for it, but it's a nice hotel, so it's okay. That's a good pay. So I asked for help, right? And where's the? Is this it?
I mean, you can get mine. A new one, a new.
So I asked for help, and I tried this. Actually, it didn't work. So don't try it. It's not the way to go. So 40 years. So let's go back. I don't have an outline because my intention is to confuse you. If I put an outline, you will be able to follow my flow. So I will just simply go back and forth. You know, this is the paper Andrea mentioned. This is what I actually call what should have been the second paper. And I will tell you why this should have been the second paper and the second paper should have been the first one. And that's because that would have been the natural way to present this story. So we see here December 12, 1983. I arrived to Bell Labs in March 1982. That's, for Argentinians, that might mean something. I mean, I got there and 2 weeks later, the military junta decided to take over the Malvinas and started a war with the NATO, right? And I was just arrived at Bell Labs, so people at Bell Labs, and I was paid by Argentina in that also. So it really, people really helped me stay there because from Argentina, what they would say, well, just come back. And then, what I want to tell you, well, 2 days before this, there's something Argentinians also remember, December 10, started our 40 years of democracy. We're celebrating this year. So what I will be doing is trying to condense you. You see, I will show you a timeline like this, and I will show you what happened in Argentina at a given time, what happened to me today, and what happened to the Ultra Fast community. And I will try to show you that something I noticed preparing this talk is that what happened in Argentina in the 70s and 80s actually tailored the evolution of the Ultra Fast science. And I will try to show you it is so. So, if we are celebrating 40 years of democracy, it's because before that we didn't have democracy, right? We had a financial dictatorship. And if you go to the School of Science, the first building, just to the right, you will see a wall dedicated after, this wall was painted 40 years after the military coup that was March 24. So if you have been in Buenos Aires last Friday, you probably saw a large demonstration in the streets because we are still fighting to get, what is it, justice for the 30,000 people that disappeared during our military dictatorship. That was a financial dictatorship. So you have these names painted in the walls. These are the students, graduates, and personnel from the School of Science. Not all, there are more than these. This is just the one that they have listed when they painted this 7 years ago. But these are just names and dates, and these were actually people with feelings, with relatives, with loves and hates and whatever. And I would like to honor them just by choosing a few of these, the ones I knew or knew something about them, tell you very short stories so that you can understand that they were really human beings behind these names. So I'll start with this one, this couple here. These are Federico Álvarez Rojas and Hilda Leikis. Federico Álvarez Rojas was a physicist. Is there anybody from Campinas here? No, I think there isn't. Okay, you know Fernando Álvarez then. Okay, Fernando Álvarez is his brother. So, I didn't know them, but I knew about their case because they had 3 children. Fernanda was the oldest one, she was 13, then there was a 10-year-old and a 2-year-old boy. One day at Counselor Institute, one of our mentors, Alfredo Burgos, and said that he had found the 3-child alone at home because their parents had been kidnapped by a mob called, they used to call them a task group. They were actually police and armed force officers that would just go all night, take people out of the house. and just left the 3 kids alone. And Alfredo Burgos and his wife were friends of his family and actually went there to invite them to a birthday party when they found them alone. And they contacted Fernando Alvarez so that Fernando took them on Thursday. Actually, there's a little more detail. When I went to Campinas and gave a talk on Mucha Fast, I met Fernando. He told me other details. Like, actually, Fernanda went with her sister, took a taxi, and went to see a relative to tell her what had happened. That relative paid the taxi driver and sent them back and left them alone in the family. So that gives you a hint of how terrible the situation was. So, okay. Now, the question is, how did I get involved in post-compression and things like that? And it's funny, I was at Bell Labs, but I was working in nonlinear relaxation mechanism in semiconductor lasers with John Heritage. But he gave me the freedom to work with other people. You know, you heard things going around. And they had in the next door room, Chuck Shanghas and Dick Ford had the colliding pulse mode blocking laser. That was the 100 femtosecond laser, a dye laser with a satellite absorber. And it only worked with one combination. And that was funny. I mean, it was difficult to understand. So I said, well, I remember from my PhD that I have some equations that might describe this. And I wrote down this equation. So this is the electric field, this is the slowly varying envelope, this is the phase, this is the carrier frequency, and this is the equation you have to solve to find a solution. Okay? It doesn't seem very simple, but this equation, taking this real, only the real part, not phase term, and only the, sorry, this is shifted. Taking only the real part of this equation, already Hermann Haus had solved that. This is satellite absorber solution, the second hyperbolic solution you all know. So I worked on this and worked for a long time. And after a few months, I came with this solution. And why I'm showing this is because this triggered the prism stuff, and I will show you why. And this solution, you know, I went, once I visited Hermann Haus at MIT, and he asked me, how did I come up with this solution? Of course, he probably had written this equation before. He just dropped these terms because he couldn't find the solution. So, how did I come to that solution? Well, very simple. I was driving to Holmdel. This is the Holmdel building in Bell Labs. And I know I can Google it. I didn't keep the maps, but I live here at Old Bridge. I drove this way. And when I was going along the 520, you know, I figured the solution out. That's what I told Hermann Haus. I don't think he was very happy with that answer. But actually, that's what happened. I mean, you take some time away. You know, what's good about driving is you don't have a pencil. Well, I know some people who do drive, nor with a cell phone. But you have no pencil, all you can do is think. Now, be careful about that, because 2 weeks before leaving Bell Labs and returning to Argentina, I placed an ad to sell my car, right? But when I was going along this road, crossing this intersection here, a brand new Cadillac came out of the stop sign and hit me on the side. Fortunately, nobody was injured. My wife also worked at Bell Labs, so we were going together. And I was able to sell my car to the insurance company. So it was a fast sale. But, of course, I had to rent another car, went back home. My daughters, they were 5 and 6 years old. They were so happy we had a new car. So you see, it's a matter of perspective. A few days later, we had everything packed in our living room, all cargo boxes, because they were going to be shipped the following day to Argentina. And a pipe broke in the upper floor and flooded our apartment. So it's okay. So they called us at home. We went back home. We picked up our daughters that were with a neighbor, and after school they would stay with the neighbor for a couple of hours. And I told them our house is full of water, flooded. And my smaller daughter, Sandra, the one she mentioned there, was a mathematician, opened her eyes wide and said, "Can you swim?" Well, she's still swimming. 2 weeks ago, she ran an open water race, so it's okay. So, as I said, I was working on this. This is my notebook, and my horrible handwriting is horrible now. I can't read it. So I can keep my notebook, but I can rarely read my writing. So this is just the date I started with this colliding pulse mode looking. That's April 1983. And what happened when I found that solution, it came with a problem. Is when we place a prism in the cavity, we can't tune it. You just put it and you just change the pulse width, but you can't change the laser. And so I tried to think what happens when you put a prism in a beam, and everything is here. Just one page in the notebook, and that's the prism compressor. A prism will add, and a cavity will induce a tilt that depends on the wavelength, and can be written as a phase filter. So basically, when you develop this, the K vector will depend on alpha, and alpha will depend on the frequency or wavelength. You have a phase that depends quadratically on the wavelength, and that's the limit state. It's going to be negative because there's a square, this L is positive. So I went with this solution, told people at the labs, hey, this is what happens with prisms. I have no idea. People have been struggling, trying to understand how to get negative compression, and they have discovered already the prisms. So, actually, about 15 years later, somebody told me when I was at the Clio conference, and I can't remember who it was from the labs, that after I said this, they had a private meeting. You know, I was a postdoc from abroad. Only people from the group that belonged to the company to discuss if I was insane or there was anything true about this. So, let's go back to the timeline. So, this is important for the young people, and I'm trying to motivate the young people. Don't feel frustrated if they think you're insane, even if you are insane. So here you have the timeline just to keep you in order of what happens. So here you will see the prism paper was received, the democracy started here, the group delay dispersion. So you see how Argentina really made a difference. So, and I will tell you why. Now, why didn't people believe the prism would work? Because of this guy, Tracy. He had developed a grating compressor. 1969, a long time ago, right? So now, 1969, let's go back to Argentina. What was happening in Argentina in 1969? It turns out to be important. I was at high school. Argentina launched, you know, the first astronaut to outer space. Few people know that. Anybody knew this in the audience? Nobody knows it. Because our history was great. And recovered alive. He passed away in a hospital in Cordoba. This rocket was built in Cordoba and was launched in, what was the name of, I don't remember the name of in La Rioja, Chancay. What else happened in 1969? An Argentine car, the Torino, built by Industrias Kaiser Argentina, designed and built completely in Argentina, raced the 84 hours of Nürburgring. That was the toughest race in the world. And it was the car that made the largest distance in 84 hours. So showing that our industry, our car industry, was competitive with, you know, they raced against Porsche, Alfa Romeo, or whatever car you could think. Now, what happened with this industry was bought by Renault, and during the military dictatorship, they stopped manufacturing Argentinian designed cars. Now, what else happened in 1969? People went to see we had another dictatorship. It wasn't the one in the 70s, this was another one, the previous one. And people went to the street, started demonstrating against the dictatorship, and started the decay of that dictatorship that ended up in a very short interim of democracy in 1973. So, okay, we have this timeline. I wrote this Córdoba Cube because the Torino was built in Córdoba. Córdoba is a province. The rockets were built in Córdoba, and people went out to the streets in Córdoba. That's how Córdoba used to be. Is anybody from Córdoba here? What happened with you guys? Okay. So, let's go back to Tracy's compressor. Why is he guilty of this fact that people thought that the prison wouldn't work? He does beautiful work. He studied it very meticulous and studied the phase terms introduced by the ratings and the path, and then he calculated the group delay dispersion. And I put some colors on it just because on those days people published in black and white. But figure caption. This is one of my messages for this talk: is look at the figure captions. He said in the figure caption, since the path length for lambda prime is the red, right? Is greater than that for lambda, longer wavelength components experience greater looping. This was engraved in the ultrafast community for 14 years, thinking that I always use transmission grating because it's easier to understand what's going on. It's the same thing. Red has a longer path than blue. Blue has a longer path than the red. Prisms won't work. Now, I was just wondering, if I didn't go to Bell Labs, and I was an Argentinian that had not read Tracy's paper, because we didn't have much access to publications, right? How long would it have taken the community to figure out that the prisms did the same, and that angular dispersion is really what was relevant? So nobody believed me, so they assigned Jim Gordon to follow my calculations to see if what I was saying made any sense. And that's how I started interacting with Jim Gordon. And you see, several months later, I was able to write it in the notation they were used. Group velocity dispersion is related to the second derivative of the optical path with respect to wavelength twice. This is horrible. But that's the way they used to think about it. And after writing it this way, that first paper came out. But the second paper was writing it the other way, the simple way. And the first way we thought about it. So, this was the second paper that should have been the first paper. And you can see here, even in the abstracts already, I just blew it out. It is shown that negative contribution to the group velocity dispersion always accompanies angular dispersion. It's as simple as that. This was the first idea, this should have been the first paper. But it took me months to convince people that this was a mechanism underlying ratings and prisms. So let's go back to the timeline, long paper received. Something else happened those days. Not only I crashed my car and my apartment was flooded, AT&T was split by Judge Green because of the monopoly. The Bell system was a regulated monopoly, and they had some controversial practices regarding other long-distance company. And AT&T was split. Well, I was working with John Heritage that they decided to build a facility for research for the Bell companies, and then Bell Labs stayed with AT&T for the long distance. So I was ripped apart. I was working with John Heritage. I went to Bell Core, and Chuck Shank and Big Four stayed with Bell Labs, and it wasn't clear from January until March I left for whom I was working. But just to keep that in mind. Notice that the paper was received the same day I was flying back to Argentina. And this will be important for something I will tell you later. So let's go back to this to show you the terms that disappeared that I wanted to mention. If you have, blue going at this angle, green this, red this, you have angular spectral dispersion. The phase going from O to or 0 to Z will, will have the K vector will be projected in this direction, and you will have a shorter phase delay for those coming out at an angle. So this is just a phase delay that depends on the frequency because the angle depends on the frequency. So you have a time delay that looks like this, and a time delay dispersion that looks like this. This is complicated. But you're looking along the theta equals 0 direction of the post-propagating. So what happens? These terms go to 0, cosines go to 1, and you're left with this simple, that's what appeared in the picture. The time delay is just Z over C. That means the group velocity is the speed of light. That's great, You feel well with the speed of light is the speed of light. I make you feel uncomfortable in the light. And the time delay dispersion, as I said, is always negative. And this will be important for something I will tell you later. So, you got these terms that disappear. Now, when I use the term disappear, I try to go back and honor again those people that disappeared. So let me rescue another man, Gerardo Strahinevich. Gerardo Strahinevich was a classmate, studied physics. He was doing his PhD, his master's thesis. The last time I saw him was because he called me, he wanted to discuss some algebra problems because he was teaching algebra, and I was a PA in algebra and he had some doubts. A mob kidnapped him from the entrance of the Atomic Energy Commission. And in plain day, this wasn't at night. They took him away, his fiancée was also disappeared. And his sister was also kidnapped, and she was tortured, raped, but for some strange reason, she was set free. And she went to the US, where she became professor at San Diego. But she wrote a beautiful book dedicated to his brother. The book in Spanish is called Una sola muerte numerosa. I just translated it to English, A Single Numerous Death. This is her name. You can just Google it and download it if you want to read it. It starts with a poem. This is the first lines of that poem I translated. When they stole my name, I was one, I was hundred, I was thousands, and I was nobody. And then it was my face deprived of gaze, gesture, and body. Well, you can go on, and this is a beautiful book dedicated to the memory of his brother. Now, I told you theta is 0. Of course, you're propagating along the beam. What happens if theta isn't 0? A lot of terms appear again. And that's something I wanted to introduce just to put some excitement here. When would theta be different from 0? Well, a Bessel beam. A Bessel beam, for those not familiar with this, is just a superposition of plane waves distributed in a cone, all the K vectors distributed in a cone uniformly. So, when you superpose all these plane waves, what you get is an electric field that goes KZZ and has a Bessel function profile in the transverse direction. It looks something like this. This is called diffractionless beam because it's the same all along this line. Of course, this carries infinite energy because plane waves carry infinite energy. If this is our Gaussian beams instead of plane waves, it will last for a while. But this doesn't diffract until it finally breaks into a cone of light. So now these terms are no longer 0, and we have to keep them into account. How do you create Bessel beams? The first way, this was Ellerly's and co-workers' proposal, was a ring. Now, how do I create a plane wave coming at an angle just with a point source at the focal point of a lens? This point source will be converted into a plane wave on this side, and every point source in that circle will be converted, in that circular slit will be converted into a plane wave, and this will generate a vessel beam. I will show in this case, if there's no chromatic aberration in the lens, it could be, there are other ways to generate this. There is no dispersion, I will show you, you will get fast light. The other way to generate that is a holoaxicon or circular grating. In this case, the derivative of the angular respect to frequency is less than 0, and you get slow light. I will go through that in a while. The most common way to generate vessel beams are axicons, those are conical prisms. And with this, I will show you you can get slow or fast light. There's another way to build this type of beams, and that is a reflected axicon. That is a cone mirror, right? Now, what happens when you put that here? Because the derivatives of the angles with respect to frequency are 0, there's no dispersion here. The time delay dispersion is 0, and the delay is z over c times cosine theta. That means the group velocity is c divided by cosine theta is much larger than the speed of light. So if you felt comfortable with the pulses propagating at the speed of light, these pulses propagate faster than the speed of light. It could be much faster if cosine. What would happen with this? Let's say you have a gas. You have to analyze what happens if you have a refractive index. But if you have a gas, for example, that's generating harmonics, the harmonics, you have a polarization of the media that's propagating faster than the speed of light. That's Cherenkov radiation, but it's coherent Cherenkov radiation. So your harmonics will be a vessel beam, propagating just overlap to this vessel beam. I'm just trying to think of other applications. No, with a grating, you know, a grating will have a radial k vector that's 2 pi over the distance, and then you will have dispersion and second order terms, and your time delay will look something like this. It's not very simple to understand. Well, what do I get out of this? So let's put examples. If tangent is 1, the group velocity is the speed of light divided by the square root of 2. And the group delay dispersion is huge, is the time delay divided by the carrier frequency with minus sign. But if the tangent is 10, your group velocity is 10 times smaller, you have really slow light. And your group delay is huge. So let's put an example, 800 nanometers, you know, this is a typical one. This would be the dispersion you would get. A 40 femtosecond pulse would have a period on Z that is a wavelength, 8 microns, so 10 times increase in the wavelength. But the special length of the energy will be 1.2 microns. So your pulse is shorter than 1 wave. And because of the large dispersion, after 1 micron, the pulse width will double. So you have huge temporal focusing. Let's put this in, you know, a little bit of colors, right? Tangent 1, the group velocity is just 30% below the speed of light. This is the distance, this is the time. This slope gives you an idea of the group velocity. Tangent 2, tangent 5, now you can see the time focusing. You see that if I move away from 0 where the pulse is focused, the pulse has broadened. Tangent 10, and you have even larger time focusing. Now, you can't go above this, and the reason is, already for tangent 10, for this pulse, you are clipping part of the spectrum because not all the spectrum components are diffracted, because some are just advancing work. So you can't go above this, so actually, you get a little worse than what was predicted before, because it wasn't taken into account. Now, what happens with an axicon? With an axicon, the dispersion isn't very large, right? So what you want to do is increase the angular dispersion. We know that angular dispersion provides time delay dispersion. So if I want something And that's why the holoaxicon is so strong, because it has a huge angular dispersion. But no, the sign matters, right? Because there were 3 terms more in the time delay dispersion, depending on the sine and the cosine, and they could balance even different signs in the delay dispersion. So how can you increase? Well, that first paper on angular dispersion creates group delay dispersion also had this telescope in it. And what I was showing you with this telescope is that from this focal plane to this focal plane, this ray has the same optical path as this one here, so there is no dispersion. But you can magnify the angular dispersion. If you magnify the angular dispersion, you get an increase of the dispersion that comes from a prism. Well, that's okay for normal prism, but not for axicons. Why? Because you magnify the tangent of the angle, not the angle. And when you look at the time delay dispersion, you get something like this. And let's just put some examples. 30-degree axicon. Let's make it pure silica or dense glass SF11, for example. And you can see that the group velocity divided by the speed of light will cross the one line for the SF11, and depending on the magnification, we go from slow light to fast light, while the fused silica you would only get slow light. But when you look at the time delay dispersion, the thing is inverted. You know, the complex terms there. You actually get more dispersion, time delay dispersion from fused silica than from the dense dispersive glass. But that's just because of the particular angle we chose. So there's a lot of work to do. If you're interested, I won't do it. And this is the time delay. You see this complicated term. It has 2 signs, and you have different contributions, and you have to prove it. So, but as I told you, I had this in that paper. I remember when I was, you know, in the middle of sending this paper out, and my car crashed and the flood, and the company split into parts. Chuck Sham came into my room and said, "Hey, Oscar, is there any way to change the sign of the dispersion?" I said, "Come on. You've been dealing, you wanted negative dispersion, now you're asking for positive dispersion once I get negative dispersion." And I explained, no, there's no way, because distances are positive and the dispersion is square, so this is always a negative term. Wrong. After he left the room, I noticed that what is called a Martinez stretcher compressor, that if you went closer to the lens from these focal points, you have an effective negative distance, so the distance is kind of negative. And this was in the paper. Another important result shown by equation 8 is that the effective length can have negative values, therefore going positive values for the nuclear dispersion. I added this to the paper, sent it out, so you were wrong. The Martinez stretcher actually was only here, not in that paper that everybody quotes. And what was my mistake? I didn't include this in the figure, So, you know, it disappeared. I left, you know, I sent this out, repacked all my belongings so they could be shipped to Argentina, went back to Argentina, and started new projects, right? But you know, this compressor, you've seen this, right? I mean, it hurts your eyes, right? What happened here? Yeah. You know, this telescope has a tendency to disappear. So now it looks better. Okay. Well, beautiful drawing, but wrong, right? Mine was a horrible drawing, but it was right. You have to choose. It might be better to have a beautiful drawing even if it's wrong. It depends whose attention you want to catch. So, back to disappear. Daniel Vendersky. Daniel Vendersky, yeah, we studied together. And the mob took him from his house. You know, his mother wanted to go with him, and they didn't allow her to go. He never appeared again. He got his thesis finished, his master thesis finished, and almost 20 years later, I was a professor at the University of Buenos Aires, and his thesis advisor asked universities to evaluate the thesis and give him a post-mortem title. And I was lucky enough to be designated as one of the members of the committee that judged his thesis. So he finally became a graduate. So this is a paper that Andrea mentioned and everybody quotes on Martinez Stretcher, but this was many years after that early 84, March 84 paper. And why did it take me so long to get here? Well, just because I was building a new lab in Argentina. And this is another paper I had out, see? November 86. The reviewers took a long time to send it back saying I should quote a different paper that wasn't quoted. I sent back, and finally it was accepted. You see, revised in March 16, 1987. But actually this was in my notebooks long before. And actually, at this time, I went for a short visit in January 87 to Belcourt. John Hayden invited me for a couple of months. And I visited the labs, and Chuck Shank and Brito Cruz was there in those days. They were trying to chill post-amplifier with dilaser. They didn't find a way to chill before the Tracy compressor. And I said, well, I'm working for the competition, I can't tell you. But I had this, and actually I proposed this to Andy Weiner, but he didn't have a high power laser to try it, so we just didn't try it. I mean, if Bell Labs invited me instead of Belcourt, and actually they were planning to invite me when they found out that I had been invited by Belcourt. Maybe Chuck Shank would have gotten the Nobel Prize. Right? So, you see, those things happen, but on those days, well, this was Gerard Moreau paper, so you can see the timing, or the timing, June 87, received March 87, so at the same time my paper went out. But this is the one that's cited, right? But what was I working on? I was working with Mario Marconi, this was his thesis, on Q switching and using a post-Yak laser with a Kelvin with a cell. And we noticed, and this is essential, that when placing the focus cell into initial stable, we used an unstable cavity that became stable by the Kelvin's focusing. But if we started with a stable cavity, we got Kelvin's control. Now, this was published August 84, March 87, but actually what happened? Mario left, finished his PhD, went to work with Jorge Roca, so he didn't work in this anymore. I was planning to keep working in this, so I tried to purchase a CW pump, Yak laser. I could do more working in CW welding. And there was a corruption act at my institution. The lieutenant colonel in charge of the purchases doubled the price of a $2 million bag of equipment that the institution was going to purchase. So I went and started, wanted a procedure to be started to investigate this. And of course what they did is just took the page I had signed asking for this laser. The first thing they told me is, you won't get your laser. So I said, I don't want my laser, I want this to be investigated. So they tore that page I had signed, replaced it by a page signed by somebody else, and I had to leave the institute. So I couldn't continue with the Caroline Moldokin, but it was patented by Cochran in 1992. I asked Luis Pinelli. Luis Pinelli was a friend, is a friend, that used to work in CITEC, institution. He knew our work. And I asked him, how did you patent? He said, we quoted your work in the patent, so you can see it here. Right? No. Typically, when you say reference cited, this is the list, then you go into the patent and you expect to find it somewhere described. It isn't. It disappeared. Some lawyer just took that paragraph out because they thought they wouldn't get the patent if they saw this paper, but they forgot to raise this part. So, okay. So you see, I had to move to Atomic Energy Commission, where I started work with Juan Chilla on that what she mentioned, the first way to measure the amplitude and phase of femtosecond pulses. That was Juan's thesis. So you can see here Magnus' work and the patent later. So something else that disappeared, so let's go back here. Jorge Vadillo, what I have to mention about Jorge, I found him, the last time I saw him, I just crossed him in the street downtown. He told me he was working for an oil company as a consultant. And then, like almost 20 years later, somebody contacted me and said that his son, that was 4 years old when his father disappeared, wanted to contact people that knew his father, because in his family it was a taboo, nobody spoke about his father. And he had no profile, he wanted to know what his father was like. So, that's the time what I want to tell you about this. Other terms have disappeared. Matrix formula for Hooke's compression. This wasn't very nice, but it works. 3 by 3 matrix to propagate beams, where these terms are related to misalignment. F can take into account angular dispersion. And what's interesting about this is you can keep it to any order. You don't have to keep it on to second. And the other terms A and B. The problem with this formalism, A and B, there's a typo here. One of my students discovered that typo, but nobody ever used it because it was difficult to use this because you had to multiply the matrices, but you had to keep the phase terms in between. And pretty soon, this came out, and this is a well-known rate-pulse matrices, and well, the problem with this is that they work perfectly. You only need one matrix for the entire system, but it only keeps terms up to second order as an efficient teaches, right? Theta squared, theta times f, f squared. You can't keep these terms, even though they are first and second order in the frequency shift. So there are a lot of things lost because of that. And because there are things lost, I just want to remember here, Eduardo Martinez, this was a disappear square because he actually was not listed here. So if you want to see his name listed somewhere, you have to go a few hundred meters from the university. You have his memorial park, just by the river, where his name appears here. I remember studying with Eduardo. I studied electromagnetism. I would go to his house in Gamma Mejia. You would really appreciate what I would say now, but I doubt many people would understand that. At that time, I started dating who later became my wife. So I would go to study at Gamma Mejia, then I would take the 343 to Florida. So for those that know what that means, just check in Google how long it takes to get. But you know, I was from the capital. I mean, that was outside. That was far enough already that I thought that was reason. That was a close lot. But last time I saw Eduardo was when he asked me to join him to look for a thesis advisor at this company here, Fat Electronics. I don't know how many people know this company. Well, this company made scientific calculators we used in the university. They also made pressure-resistant electronic machines that they exported to Europe and competed with Olivetti. And In 1975, they had a Beta microcomputer called Series 1000. I believe they had the same processor, Apple, that was founded in April 1st when this company was shut down by the military junta. Was founded. So you can see, he wanted to do in applied work his thesis on this company. And I tried to do my thesis in solid state physics with Aaron Pinchuk. Aaron Pinchuk passed away last year. He was a professor at the university, but he was fired, and he was working at Atomic Energy Commission, and the university did not allow me to go to work with somebody that was fired from the university. All my professors, even the Nobel Prize, Federico Leloir was fired from the university. And Aaron Pinchuk then had to leave the country. Actually, he was visiting Max Planck Institute with Manolo Cardona when they told him, don't come back or you will disappear too. So he went to Bell Labs, and actually he recommended me to John Heritage for my postdoc. So imagine if this didn't happen, and I work in solid state physics, I wouldn't have gone to Bell Labs, and who would have discovered the prison compressor? If everybody there read Tracy's paper and the figure. So, just finishing. Keeping those terms I just told you, this is something I proposed Jorge, but we didn't come to a very nice solution, but just to give you an idea. This is just a grating, you disperse and a mirror, you focus, and you have different components focused here, but at a certain distance, you will have, this will blow out due to diffraction, and you will have overlapping spectra here, and at a certain distance, you have to calculate what the phase of your pulse looks like, and so you have this, you keep higher order terms in your dispersion, and you calculate that phase, and when you do that, you will have terms that are proportional to your frequency shift. This is time delay. And frequency shift squared, this is the time delay dispersion. But it depends on x, the transverse direction, and it also depends on z. So depending on z, you will find surfaces that have the same chip. I call them isochip surfaces. And if you make that surface coincide with your target, then you will have your pulse compressed at the surface if you prepare your initial chip adequately. And you can change the group delay depends on x. So you can have traveling wave excitation if you adjust this term here. And this is a narrow term, a quadratic term. Just to give you an example, with a 10 centimeter beam and a 10 meter focal length, you can get a 1 centimeter beam with this grating that is an error due to the quadratic term in the traveling wave excitation of 40 femtosecond arcs. So with this, I almost finished. When I was about to upload, and it will take me 2 extra minutes from the 50, it's already 50 minutes. But I'll take 2 extra minutes because when I was going to upload my talk, I was hearing the radio. I don't know if anybody recognizes this here.
Eternauta.
El Eternauta. This is an Argentinian comic, El Eternauta, the Eternauta, written by Oesterheld. I heard in the radio that Netflix was going to take it to the screen, and they were talking to Ricardo Darín for the main character. And I remember Oesterheld studied geology in the School of Science, and he also disappeared. I doubt Netflix will remember that. This is Oesterheld with his 4 daughters, 20 years after this picture, the family picture. Not only he disappeared, his 4 daughters disappeared too. 2 of them were pregnant. And his 3 husbands of these 4 daughters also disappeared. So this family was just ripped apart. And I thought I had to add this when I heard that Netflix was going to take this too. So final remarks. I have no conclusions from this, but I have some few final remarks. First, rephrasing Richard Feynman's "There's plenty of room at the bottom," I hope it made it clear that there's plenty of room And you know, knowledge is a fractal, and you're always at the edge of knowledge, no matter where you're sitting. Read beyond the figure pattern. At least if you're one of the authors. Then the other thing, it's good to take some distance when you're working on something, stay away for a while to rethink, but walk on by. You know, there are Cadillacs talking to you, waiting for you to cross the road and jump on it. What's your context? I mean, when I prepared this talk, I found, you know, hey, so many things happened that would have spoiled me going to the lab. I mean, I could have studied solid state physics. I could have gone back because of the Malvinas War, and so forth. And in the meeting, they could have concluded that I was actually insane, and it couldn't have been far from reality. So, and I want you to think, how long would it have taken the community to figure out that the prisons would work just like the Philippines? I don't know. Until, you know, Tracy's paper was lost somewhere. And the last remark is to understand, don't look at the hand as hard as you, just check for profits. And with this, I want to thank you very much.
Does anybody want to say?
We never met. I heard about you when I was a summer student and later on worked at Bell Labs. And all I can say, I'm honored to finally meeting you. And by the way, they definitely told me that you were the mastermind behind it. So, just for your record.
No, yeah.
Just one more comment, and then we invite all of you to talk during the aperitif we are going to have.
Yeah, well, first, congratulations to the organizer for trying to do this. This is excellent and long overdue. Basically, right? I mean, I have known Scar for 40 years. Man. Basically, we met when we were doing basically our degree thesis, right, on the same institute, and then we had only one phone at that institute, right? And then we had to make phone calls, and he was in front of me, right, and I see his note, and he had written O'Higgins, don't remember the number, but a certain number of certain apartment building, and we were just buying an apartment in that building. And I said, how come you know that address? And he said, I'm buying an apartment in that building. And I said, gee, this might be a scam. Someone is selling both of them the same apartment. but they were different apartments, right? Ours was like on the 14th floor, 15th floor. And Oscar already had, 2 young daughters. This was before Bell Labs. Basically, the lovely daughters. I just come down to his place, I would have breakfast, then go to the bus. I walk to the bus, and from there, go to talks on physics and other things, right? And get to the institute. That's how we met, right? And through the years, we had different collaborations. At one point, he spent summer at Colorado State, right? And then we were able to do some work together, and I was also able to work with him and Nelly, his wife, right? So we applied techniques we were developing right to her work on solid state. So I'm very happy that you organized this, right? And certainly want to congratulate Oscar for his tremendous contributions to the field.
We are going to continue celebration of the aperitif in the sponsors room. First, let me give Oscar a small token of appreciation. Before we leave, there was some of his co-workers.
Thank you.
So some of his co-workers wanted to say a few words, so and then we go downstairs.
Yeah.
Okay, good afternoon. My name is Jorge Torga. I am working in National Technology University near Buenos Aires. I want to say a few words about Oscar. I met him as a student in the 90s, and we worked together in my PhD, and after that for several years in his lab. It's difficult to sum up what he meant to me and to many colleagues and disciples who have worked with him and learned from him. And I think it's fair to say that he is a great teacher. He was our mentor because he inspired us, made us see things differently, and showed us interest and beauty in things we hadn't considered before. I say this is in the context of optics, photonics, and science, but what's more important, I think, he was a teacher of life. It's difficult to explain in a few minutes. I only prefer to say words like generosity, honesty, support, encouragement, keeping one word, speaking clearly and without reservation, and upholding values. Those words, I think, are Oscar. Somehow they are become part of me. And there are many times when I have to make a decision or take action today, and I use his example as a guide, imagining what he would have done if he were in my place. It was a great pleasure and pride to have worked with together these years. Thank you, Oscar.
I'm Gabriel Vilmes, and I would like to say something about the technological contributions of Oscar. I met Oscar in the early 80s, and we had a strong interaction at national meetings and conferences. In the early 90s, we worked together on applications of pulsed photoacoustics to determine phase change thresholds in metals and the crystallization dynamics of amorphous materials. In 1993, we created, along with Héctor Ranier Sandoval, the Photophysical Division of the Argentina Physical Association. Now it's the Photonic Division. It was the first division of this association. In the second half of the 90s, we began working on a demand from the Argentine steel industry, the measurement of surface cleanliness, and we invented a method and an instrument based on laser ablation and acoustic or optical detection. We obtained 4 patents, one in the United States, and we won the first National Innovar Prize in the National Innovation Contest of Argentina. Based on these inventions and other ideas, Oscar created the company Tolket. Our last work together was the invention, with other researchers, of an instrument for detecting COVID and other virus, now in the validation stage. Oscar is a brilliant, general scientist, imaginative and rigorous, and highly creative experimental phases. But he is also a scientist committed to the reality of his country, to human rights, and to the development of a national science that solves the problems of our society. Oscar. It has been
Oh, you were talking about me?
yes, it has been a pride to have shared the projects and works that brought us together with you, and a privilege to have learned something new from you at every opportunity. Thank you very much.
Now we invite everybody to go to,
Okay.
to get a drink and some snacks in the